Welcome to Six Sigma Black Belt, Course 5, Module 4, Non-Parametric Hypothesis Testing. In statistical analysis, we often encounter situations where some of our assumptions are not met. While it is true that departures from some assumptions maintain robustness of the statistical test, in other situations, we need a more conservative alternative. Non-parametric techniques addresses this eventuality. The non-parametric tests are often called distribution-free, since they make no assumption regarding the population distribution. Non-parametric tests may be applied to ranked data, not specific in any continuous sense. Because the assumptions are far fewer, non-parametric tests can be applied to more situations and data types. Non-parametric tests do tend to waste information and are therefore less efficient. Mood's median test is used to compare medians from two or more groups. We seek to determine if they are different. The null statement is that the medians are the same for two or more groups. The alternative statement is that the medians are different for two or more groups. Mood's median test is a variant of the chi-square contingency table test. Because the Mood's median test is non-parametric, a tally is taken based on the number of values greater than the median and the number of values less than or equal to the median. Let's consider this example. We are given data for three groups. Assume alpha is 0.05. The first step in this process is to find the overall median of the data. Tally the number of values of each group that are greater than the overall median and the number of values that are less than or equal to the overall median. These totals are found in the table in the upper right. Use this data to find the chi-square test statistic. Note that there are 3 columns and 2 rows. This gives us a degrees of freedom of 2. The test statistic is 1.0095. The critical statistic is 5.991. Therefore, we will fail to reject the null. The medians are the same. Levines test is the go-to procedure for determining homogeneity of variances. Although it is parametric in nature, it is preferred over other related tests due to its robustness under violations of normality. The null statement is that the variances are the same. The alternative statement is that the variances are different. Some data manipulation is required before running Levines test. The absolute value of the residuals of the group means are calculated. A residual is the difference between the data value and its respective sample mean. An ANOVA is then conducted on the absolute value of the residuals. If the group variances are equal, then the average size of the residual should be the same across all groups. Recognize that we must assume that the assumptions for ANOVA on the absolute value of the residuals are met. Levines test is often used before we assess the sameness of the means. If Levines test shows significance, it is recommended that we move to Welch's t-test. Welch's t-test is more conservative and does not assume equal variances. Let's look at the data from the previous example. Again, assume alpha is 0.05. We calculate the means for each column. In the bottom left table, we use each mean to find the corresponding absolute value of the residual for each data point. The ANOVA analysis is shown in the bottom right. The p-value is greater than 0.05. Therefore, we fail to reject the null. The variances are the same. The sign test is the most elementary and least efficient non-parametric test. It involves converting data values to positive and negative signs, and then testing to determine whether either sign occurs significantly more often than the other sign. We use this test when assessing matched pairs, assessing the majority with nominal data, and comparing a median to a target. The only requirement for the sign test is simple random samples. The test statistic follows a conditional approach. If the sample size is at most 25, we use the smaller number of the frequency of the pluses or minuses. If the sample size is greater than 25, we still calculate X as outlined, but we convert X to a z-score using the formula shown. Let's consider this example. Suppose we look at the heights of 117 males. We find the following results. The null is that the median is equal to 76 inches. The alternative is that the median is less than 76 inches. We have 71 values below 76 inches, or 71 negative signs, and we have 37 values above 76 inches, or 37 plus signs. Discard the 9 ties. This leaves us with 108 samples, and X equals 37. The sample data do not contradict the alternative statement because most of the values are below 76 inches. The test statistic is calculated to be negative 3.17543. The p-value to the left of this value is 0.00074807. This means that we reject the null hypothesis. The median is less than 76.